Advanced Math Lesson 12. Part A is called Angles and Diagonals in Polygons. And you see a bunch of polygons here. First thing, for any polygon, whether it's concave or convex, the number of sides is always the same as the number of vertices. The vertices are the corners, the points at which the sides connect, the endpoints of the sides. And okay, so the first thing we're going to talk about here is interior and exterior angles. Interior, of course, are on the inside. So here, here, here are interior angles. If we extend a side of a polygon, then this angle is an exterior angle. There's an interior, there's an exterior, and you can see that they are supplementary. Okay, they form a straight angle, and they have a shared side. This plus this equals 180 degrees. Those two are supplementary. Okay, we could also have extended this side at that vertex, and then this is still this angle. And this is the exterior angle that we have now. This one is congruent to that one. If we drew them on the same triangle, you see they're vertical angles. It's down there. And one other thing I wanted to point out with these, okay, we know that that interior angle, which I guess I'll keep calling I, and this exterior angle, E, add up to 180. I'll label these also. Okay, so you also know, okay, whatever these degrees are, okay, A plus B plus I is 180, but E plus I is also 180. That means this exterior angle is equal to the sum of A and B. That can be a kind of a useful shortcut for you sometimes when you're finding out the degree measure of angles in some of your polygons. Okay, so for triangles, it works that this is called the remote exterior angle. It's the exterior angle that's further away from those two. It's the same as the sum of those two angles. Anyway, so you know in any triangle the sum of the interior angles, like I said, is 180. We're going to talk about the sum of the exterior angles of any polygon. Okay, so over here we have the random one, and if we show exterior angles at all these vertices, okay, so here, 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 and here. The sum of those, no matter what your convex polygon is 360 degrees. And if you look at it this way, in the book they show a picture of a guy walking around a polygon. But if you are going the whole way around here, like add up all these exteriors, by the time you get around, you've gone full circle. You know there are 360 degrees in a circle. The sum of the exterior angles of any polygon, any convex, is 360 degrees, no matter how many sides it has. Okay, so that's what we're doing with exterior angles. Let's talk a little bit about interior angles of polygons. Okay, so here we have a 3-sided figure, a 4-sided figure, 5 and 6. And we're going to talk about the sum of the measures of all the angles inside these polygons. Okay, we know this is 180 degrees inside here. All right, now, in any quadrilateral, that looks like a rectangle, but it wouldn't need to be. we can draw a diagonal, and we have now split it into two triangles. We know each of these is 180 degrees. 180 here, 180 there. The sum of the interior angles of a quadrilateral is 360 degrees. Okay, so now we have five-sided. We have a pentagon here. That can be split into three triangles. Each of those is 180 degrees. 3 times 180, 540 degrees. Okay. Now we have 4, 720 degrees. And you can see a pattern developing here. Each time, okay, we have a 6-sided figure, we got 4 triangles. A 5-sided figure, we got 3. Each time, you can take the number of sides minus 2, and that's how many triangles you can form. Okay, so we can get a formula from this. The sum of the interior angles is this. N being the number of sides, okay, you take n minus 2, and that tells you how many triangles you can make out of it. A 3-sided figure, 3 minus 2 is 1. There's 1 triangle. A 4-sided figure, 4 minus 2 is 2. You got 2 triangles. You take the number of triangles, which is this, times 180 degrees. And that'll give you the sum of the interior angles of your polygon. Okay, so there is a formula for the sum of the interior angles. Now we're going to have another formula when we talk about diagonals, which is what we're going to do down here with these figures that are showing up again. Okay, so we were drawing some diagonals to form triangles, but that wasn't always all of the diagonals we could get. So we're going to take a look at this as well. Now a diagonal is a segment you draw that goes like through the polygon. It connects two vertices, two non-consecutive vertices, because if I'm connecting this vertex to this one, that's giving me a side. That is not a diagonal. Okay, so actually there are no diagonals to be drawn in a triangle. When you go from one vertex to another, you're always drawing a side. Okay, there are no diagonals. Here, we can go from that corner to that corner, but we can also go from this corner to this corner. So here we have 2 diagonals. In a pentagon, okay, so we did this already forming the triangles, but I could have started here, could have gone here, go here. Okay, so all the possible diagonals here, looks like I have 5 this time. So it's kind of hard to see a pattern at this point, but let's think about this. Let's say I'm starting at this point on my hexagon. Okay, so how many diagonals can I draw from that point? Well, I can't draw a diagonal to itself, and I can't go to either of the consecutive vertices because that'll make a side instead. So there are 1, 2, 3 vertices that I can never connect to any particular vertex to. I can connect it to all of the other ones. So I could go however many vertices minus 3 tells me how many vertices I can connect to make a diagonal. I can't connect to this one or to the next one or the one before it. Okay, so how many I can connect to would be 1, 2, 3 in this case. So it'd be 6 times 3 here, which would give me the 3. Okay, but there are 6 vertices in this whole entire thing, right? So then I could take this, which tells me how many any one vertex can connect to, but I take that times the total number of vertices that there are. Okay, because let's say from this point, okay, 1, 2, 3. Whoops, I missed. But I don't want to count this one twice. I already counted this one going here, right? So I can't count it going back. Each of these like to go both ways. So what we're going to do is divide by 2. So we're not counting them twice. That tells you the number of distinct diagonals. Number of diagonals in a polygon. Any polygon. Okay, again, n representing the number of sides. So these are 2 formulas we'll be using a good bit, and I know they have some similarities. Please don't get them confused. Okay, just take your time when you're doing these till you get used to them. Always take your time, but especially while you're getting used to them. Okay, now let's take a look down here at example 1. Find the sum of the measures of the interior angles and the exterior angles of a 7-sided convex polygon. Okay. So for A, it's the interiors. Let's look at our sum of the interior angles we had up in the notes. Okay, sum of the interior angles was n minus 2. We have a 7-sided, so 7 minus 2. Tells us how many triangles we can make out of that, which we will then take times 180 according to the formula. So we're doing 7 minus 2 is 5 times 180 degrees. And so it looks like we're getting 900 degrees. The sum of all the interior angles of a 7-sided polygon is 900 degrees. The calculation down there. Fill the numbers into the formula. Well, the number 7 minus 2, and then simplify it. Exterior, answer is always the same. 360 degrees. That part's simple. Always is that. Okay, that's all they wanted to know. They didn't ask anything about diagonals in that one. Let's move on. They could have. But we're going on to part B now. Okay, so this is proving the chord tangent theorem, which first we need to talk about what that theorem is. Okay, so we've already done things with inscribed angles in a circle. And let me go ahead and just sketch something here. Okay. So there's an inscribed angle, okay, and we know that this angle is half of this arc. So if this is x degrees, this angle is half of that, 1/2 of x, or x over 2 degrees. Okay, we already know this. Now, if you think about, well, let's just draw it over here. If we have, try to keep this about the same. Okay, so if we think about, here's this other side of the angle, the one ray. If we keep moving it out, 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 don't draw this yet, just bear with me. Okay, so we're going to go here, and if it keeps moving, and we're expanding that angle, seeing that this distance from here to here is getting shorter and shorter and shorter. And eventually, if you keep expanding, swinging that one side around, you're going to have, I didn't quite do it, where one of them is tangent to the circle. We'll just touch it at one point. Okay, this is a chord and this is a tangent. And the chord-tangent theorem is saying that the angle formed by a chord and a tangent is also half of the intercepted arc. Okay, so it's saying that if this arc all the way around here, we'll say that's y degrees, then this angle right here would be half of that. That's the chord-tangent theorem. And we're not only going to start using it, we're going to prove it fairly informally. Okay, so here's it's saying what the chord-tangent theorem states. The measure of an angle formed by a chord and a tangent is half of the intercepted arc. And we've got three possibilities. Case one is the chord is a diameter, goes through the center of the circle. And then we'll talk about the other cases. Let's start with this. So for example 2, we're supposed to prove case 1 of the chord-tangent theorem. Okay, so case 1 would be that the chord could be right through the center of the circle. So, center of the circle. Okay, there's our chord, and here's a tangent. Okay, tangent to the circle, which just means it touches it just at one point. Okay, and we already know that a tangent is always perpendicular to some radius. This is a radius. These are perpendicular. We also know that a diameter cuts a circle in half. So the arc is 180 degrees, but a right angle is 90 degrees. It's half. Okay, so let's label things here. I'll try to keep consistent with the book. Okay, so this point is B. Here the vertex is A, and then a point on the tangent we're going to call C. So 90 is half of 180. So yes, 90 is half of 180. So angle, the measure of angle BAC is half of the measure of arc BA, sorry. Not really much else to say about case 1. Now in case 2, let's see, the center could be inside the angle. Alright, so if the center's here, say, let's go like this. And then tangent to the circle, something like that. And we are getting an obtuse angle. Okay, this is larger than 90 degrees. But, okay, so what that means is we can split that into a right angle and an acute angle. Okay, so we're going to put our diameter back in here. Okay, it goes from this point through the center. Okay, that means this is right. And we just saw by looking at this up here in 2, I don't know how crooked, I still had that, sorry. From up here in 2, that the right angle is definitely half. And we already knew from before that that inscribed angle is half of this arc. Let me label some points again. Okay, so now this was our B, and here's our A, and here's our C, and then I guess we'll just call that D. Okay, so now we already know from case 1 that angle DAC, measure of angle DAC, is half the measure of arc AD. And we knew from before, because it's an inscribed angle, that the measure of angle DAB is half the measure of arc DB. And if we were to add these two up, that gives us this larger obtuse angle. See, DAC plus DAB, that's this whole angle. So we're going to add them. Measure of angle BAC is half of the measure of what? Okay, when we add arc AD to arc DB, that's this whole big arc. Measure of arc ADB. We've proven case 2. And then case 3 is, well, what if the center is outside of the angle? Okay. So in that case, we're going to have an acute angle. Move this up a bit. Okay, so we have an acute angle. So there's our center. The center will not be in, so our chord could be up here. And sorry, I'm going to move this again. I need a tangent. That's too rough. It's a rough sketch. Drawing not to scale. Okay, so we're going to put our, relabel this first, sorry, B, A, C again. We're going to put our diameter back in. There's our D. Okay, so from case 1 again, we know that the measure of angle CAD, okay, again, this is from case 1, it's a 90-degree angle. It is half of that arc ABD, half the measure of ABD. And we already know that this inscribed angle is half of the arc. This sounds a little repetitive, doesn't it? Okay, so because it's inscribed, we know the measure of angle BAD is half the measure of the arc it intercepts, BD. And this time we're going to subtract. If we took this angle minus this inscribed angle, we would get angle BAC, which is the one we're supposed to be looking at. So this time we're subtracting. And that's giving us the measure of angle BAC. And over here we have half the measure of. Now, this big arc minus this little arc, that's just arc AB here. We've actually proven it. This angle right here is half of this arc. It has all been proven. It's possible you want to go back over this or read it in the book just to get things solidified. But basically, you'll just be using this theorem in some of the problems. Okay, if you have a chord and a tangent forming an angle in a circle like this, you still take half of the intercepted arc to get the degree measure of that angle. And that is all we've got for the notes. See you later.